Our second presenter is actually a colleague of mine, Dr. Shaker Haji. His presentation titled Feasibility Study on a Small-Scale Grid-Connected PV Systems for the Kingdom of Bahrain. Dr. Haji is an associate professor in the Department of Chemical Engineering at University of Bahrain. He holds a bachelor degree from King Abdulaziz University, MSc and PhD from US University. And he is specialized in chemical reaction engineering, thermodynamics within application areas of renewable energy and fuel cells technology, wastewater treatment, and fuel processing. Dr. Haji has lectured in several short courses on the topics of renewable energy and fundamentals of chemical engineering. The floor is yours, Dr. Shaker.
Thank you very much for your nice introduction. I wonder if you can hear me clearly, or should I?
Yeah, we hear you clearly.
Okay, excellent. Okay, so thank you very much again for having me here. And thank you also for the attendees for joining us in today's session. Today, my lecture will basically be answering one main thing. Is it feasible for me to install PV system on my house, or in residential facility, commercial facility, or even industrial facility? However, our study is based on a small scale, but it can be expanded on other applications. This is what I'm going to talk about. We have a brief introduction, methodology of how I answer, is it feasible or not? Then present to you the results and discussion, and then few associated benefits on the top, and finally the conclusion. Okay, let's start with introduction. So we're talking here about grid-connected photovoltaic system. So the PV is connected to the grid. This system allows households to generate electricity power and feed it into the public grid. The PV generated electricity is sold to the electric utilities under various subsidy schemes, among which are net metering, net purchase and sale, and feed-in tariff. Of course, you're all aware that recently net metering scheme was employed in the Kingdom of Bahrain. Okay, so a brief introduction about net metering. As you can see here, we have, yeah, that's our meter. So we have a bi-directional electric meter. So if you consume electricity from the grid, the meter runs forward, charging you. If you feed PV electricity, so here you have your PV in your house, and you're producing energy to your house, and still you have excess, for example, in times that you're not in the house. So this excess goes to the public grid. So here the meter goes or run backwards. The household is billed for the net amount of electricity consumed at the end of every billing period, of course, based on the normal tariff, the published tariff. Then we have another scheme, which is not employed in Bahrain, net purchase and sales. Basically, here you have two meters, and everyone is unidirectional. And then here, any excess energy you are producing and feeding to the grid, that you will be paid for. Okay, at given instant, if you are feeding or producing more than consuming, at that instance, you will be rewarded, and will be rewarded at higher rate, usually compared to the tariff. And finally, the feed-in tariff scheme. Here again, you have two unidirectional meter, but in this case, as you can see, the PV is not connected to the house. The PV is connected to the meter, to the grid through a meter. So basically, whatever you produce from the PV, you're going to get rewarded for. You're going to be paid for. And as we say in Arabic, basna flus yahsin. However, this is not a scheme that is employed in Bahrain. What is, out of these three schemes, what is the best? Of course, the feed-in tariff, because you get paid, for whatever you generate, whether it is more than what you consume, less than what you consume, no matter when, where. So the feed-in tariff scheme played the greatest role in promoting the use of renewable energy technologies, including PV, in different parts of the world, and is now well established worldwide. And of course, it is because of the feed-in tariff scheme where people and companies were encouraged to install renewable energies, and therefore it drives its prices lower and lower in the market. Okay, let's go to the methodology of feasibility determination. How did I determine is it feasible or not? There are 7 steps, which I'm going to take you through. Well, the first thing to do is, of course, to identify the PV module specification. So which PV module you want to buy? Is it going to be a crystalline silicon solar cell, which is well-developed technology, or is going to be one of these new technologies with lower cost and, however, lower efficiency, which is the thin film solar cell? Of course, in our study here, we're going to go safe. So we're going to go with polycrystalline silicon. It's quite popular. It has lower cost. However, it has also good efficiency. So after determining the specification, we go into details. So I'm not going to go through the whole details. However, for example, what drives me to choose this technology is the operating temperature. You can see that this kind of technology can operate between -42 to 85 degrees C. Of course, 85 degrees C is not the ambient temperature, it's the temperature of the PV, which is black, so its temperature will go high. So I want to make sure that my PV module doesn't blow up. And the other thing I should look into is the cost of the system. So currently the market price is around 300 fils per watt peak. Of course, watt peak is the theoretical capacity of the PV module. It's not what actually produces for you. However, it's the theoretically at the lab, it produces this much, and the price is determined based on the capacity. So the current price is between 300 fils and 350 fils. That's more common per watt peak. So that's the price which I'm basing the calculation on. And then, of course, the PV has efficiency of PV module has efficiency of 14%. And after all the losses that I inquire, the temperature losses, the wiring losses, the processing losses, I'll end up with 10.25% efficiency. Okay, let's go to step number 2 and 3, which is estimate the PV panel size and system cost. So what is the size of the PV that I want to install on my house, on the roof? So here we take an assumption that 25% of the roof I want to cover it with a PV system. So that will enable me typically for a system size of 5 kilowatt peak. That's a good typical size for the house. You can go more than that if you want. And it will cost me around 1,500 BD. Okay, now let's go to the fuel, the input to the solar system, which is the sun. So we need to know the local solar data. And in the previous, of course, session, they were talking about feasibility depending on where you are and so on, many factors. So there you go. Where we are, we have to look at the solar data. So this is the solar data in Bahrain. As you can see, the solar irradiation is very good from May all the way to October. The rest of the year is also good. So it's really a good input of solar power. And you can get all of these data online from the PVGIS database. Okay, then we can calculate the PV electricity generated, how much electricity I generate. I have the input, I have the efficiency, and I can calculate how much electricity I can produce. So basically, the annual yield, this is a useful number to remember. An annual yield in Bahrain is around 1,685 kilowatt hour per kilowatt peak installed. So monthly average PV electricity generation, in this case, will be around 700 kilowatt hour. That's how much on average in a month I will produce for a system of 5 kilowatt peak. Let's compare it to what I consume as a household. For if we are a member of 5 in the family, so we consume around 4,700 kilowatt hour. So that's the PV is contributing with an average of 15% of my electricity. Okay, then we go a little bit more deeper into estimating the PV electricity cost. How much does it cost me to produce this electricity? Of course, the fuel, the sun, is free. However, you have to pay for the PV for the installment. There is a capital cost. So, and there is a little bit of maintenance as well. And there is also cost of taking a loan. So all of this makes that the production of PV electricity make it as a cost. And this is known as the levelized cost of electricity. So how do I do this? Well, I need some financial parameters. So here, for example, am I going to take a loan? In this study, I'm assuming 50% loan, and the 50% I'm going to pay it in cash. The loan is taken at this APR interest rate. So this would be the monthly installment for 7 years, personal loan. This is the operation and maintenance cost. Basically, you need some water and a cloth to clean it. And also, after, I'm assuming here, after 10 years, you will need to change one component of the PV system, which is the inverter. And this will cost around 300 BD. Based on that, we'll construct a cash flow statement. So this is a cash flow statement, which shows you the year, the month, how much electricity I'm producing per year. And if I was going to be paid for this electricity, this is how much money I'm going to make. This is the loan installment. You can see it finishes at year 7, and maintenance and cost. And of course, this is the net cash, the cumulative cash, and so on. Okay, so how do I determine the PV electricity cost? Well, basically, the question is, what is the generated kilowatt hour price that sets the net present value to 0? So I'll look at the net present value for those familiar with the finances, or in a simple word, what is the price of the electricity that makes you break even? لا لي ولا علي. يعني خلاص, I'm not making money, I'm not losing any money. So what is that price which breaks me even, breaks my investment even? In this case, where we say that I purchased the PV at 300 fills per watt peak with a total price of 1,500 BD, here the break-even price of the electricity, or the PV electricity cost, is basically 17 fills per kilowatt hour. So now we can compare this to the subsidized rates of electricity, which is 3, 9, 16 fills per kilowatt hour. And of course, you can say that obviously it's not feasible for a subsidized customer to install PV on top of his house, unfortunately. Okay, however, for those people who are paying the full rate, the unsubsidized rate, which is 29 fills per kilowatt hour, if the cost of electricity is only 17, that means they will be making saving. So how much, what will be the internal rate of return, and what would be the payback period? Also, I can calculate it through this spreadsheet. And in this case, for non-subsidized customers, the payback period is 7.5 years with an internal rate of return of 16.4%. To make sense out of this number, you know, when the days were the good days, let's say for the real estate, the internal rate of return was around 10%, 12%. So now this is even better than that. Okay, so let's have a brief discussion about the results. Okay, the first question would be, shall I buy the PV system in cash or installment? Of course, here we are varying that down payment. Again, we're assuming we're taking a 7-year personal loan. Okay, so if you put zero down payment, that means 100% of the price of the PV is, to be installed or purchased through a loan. So in this case, the price of the electricity will be higher compared to a case if you pay it cash. So you don't have to pay for the loan and the interest. So in this case, the range of electricity will be between 16.3 and 17.7 fills per kilowatt hour of PV electricity. Of course, this is based on this market price, which is a little bit difficult to find nowadays. Maybe 325 is more reasonable for nowadays. Okay, what if the price was not 300 fills per watt peak, what if the PV system price was not this much, was something different, was higher? Then this figure will show us what would be the price. So if it was 350, the price will be for the PV generator.
You have 5 minutes to go.
Sure. So it'll be around 19 fills per kilowatt hour. And for example, if the price drops, then of course the cost of the generated electricity will be less. Basically, this is an equation that you can use. I hope the presentation will be available for the listener so they can make use of it. So for the subsidized EWA customers, PV system won't be feasible until the market price gets below 150 fills per watt peak. For non-subsidized customers, of course, it is feasible to install PV system at current market price. Okay, one last thing here. We have also another figure to find out the payback period and also to find the internal rate of return based on the PV system price in the market. So basically here, if we take the current market price, the payback period is between 7.5 to 9 years. The internal rate of return is 16.4 to 12%. Okay, are there any other benefits for installing PV? Yes, there are. One of the great benefits is that if I produce PV in my house and generate renewable energy, that means I will not need that much energy from the power plant. That means we'll save some natural gas. How much natural gas will save per house of 5 kilowatt? This is the amount of natural gas which is saved. And how much that would be in terms of money for the country? That would be around 127 BD per house based on the market price of PV. What other benefits? If you're not burning natural gas, of course, you are avoiding emissions. By how much? Well, for every house, we're avoiding the emission of 5.16 tons of CO2. So you are helping the environment. And of course, also, we're avoiding the emission of other, pollutants. I would say, non-environmentally pollutants. So that's really something good. You are saving the environment as well. Okay, is there any other benefits for EWA? Yes, there are. Well, we said we're purchasing the system for 1,500 BD, and we're producing this much electricity per year, 8,425 kilowatt hour per year. This much electricity, if EWA was going to provide it to me, then it will cost EWA this much, 244 BD, based on that 29 fills per kilowatt hour cost of electricity to EWA. Okay, that's the EWA's cost. However, what it's going to bill me, it's going to only bill me for the subsidized rate, which is 3, 9, and 16. So if we take 9 fills per kilowatt hour, it's going to bill me only this much. That means EWA is losing 170 BD per year. If we multiply it by 20, which is the life cycle of the PV, then this is how much EWA will lose in 20 years. So maybe it's also in the benefit of EWA to support the subsidized customer to buy PV to install them in their houses. And this subsidy could be in terms of capital rebate. Tell the customer, okay, I'm going to pay 50% of your system, or I can provide you the interest-free loan or so. Also, we benefit EWA because we all know, Shabab, that we have a problem of peak load during the afternoon and during the night, of course. And this peak load every year is increasing. And also, we have the energy demand, which is every year increasing. So with a simple calculation, we see that if 4,600 residential PV installation per year take place, so basically I'm saying I need around 4,600 houses to install PV on top of their house, they will also contribute to as much as 5% to the estimated annual growth in the peak load, which usually happens between 1 and 4 o'clock, and also contribute with 5% to the average annual increase in electricity consumption in Bahrain. Other benefits would be I'll create some jobs in the market, and this is some estimate of the creation of job. This is related to PV, maybe also other benefits, with the awareness of renewable energy. Other businesses start taking place, like water heating through solar energy and so on. Okay, let me conclude my presentation here. So basically, in this study, an economical model was structured for the estimation of the PV electricity cost and the possible resulting internal rate of return and payback period. And it is an EWAS advantage to support the installation of PV systems for various reasons. There are also associated benefits for the PV system installation, such as production of renewable electricity to support the national grid, generation of power around the afternoon peak hour, sparing natural gas, avoiding greenhouse gas emissions, which help with the global warming, and also creation of jobs. And toward the end, I would like to thank a few people who I had very fruitful discussion with. And thank you very much for listening. If you want more information, you can refer to my published paper, Feed and Tariff Structure Development for the Photovoltaic Electricity and the Associated Benefit for the Kingdom of Bahrain. It's available online in the International Journal of Sustainable Energy, and you have my contacts in case you have any questions. Thank you very much.
Okay, thank you, Dr. Shakir, on this excellent presentation about your work, in which the academia actually investigate case study in Bahrain. So that's good in terms of collaboration with the official institutes in the future. Inshallah, more things to come.